Okay. So what I'm going to do, like I said, I'm going to start with examples that I think are probably the best example of this, like theory to policy pipeline within our field. And that is about stable matching theory. Okay, so the first thing I want to do is just set up what is the class of problems that this section is going to consider. So think that there's n doctors and n hospitals, and each hospital has one job opening. Each doctor wants one job, and I'm hoping that this is going to be the procedure that clears this job market. Okay, so what is the input to this as an algorithmic problem? So each resident, the residents or the doctors, they have strict preferences over the possible job. So for example, Dr. J might say that they like job 5 best. And if they can't get job 5, job 14 is their next favorite. They have some third favorite and so on. And each hospital has strict preferences over the possible doctors. They have their favorite possible hire, second favorite, etc. And our goal is just to clear this job market. I would like to match the doctors to jobs where each doctor gets a job and each job is filled by one doctor. Okay, so how, in practice, how might you solve a problem like this? Well, in a lot of job markets, the way it is clear is there's just a decentralized procedure. So what happens? The doctors apply to jobs, the jobs do interviews and make offers, the doctors accept or reject those offers, and then new offers get made. And eventually, hopefully everyone winds up with a job and the hospitals wind up with candidates they like. And this is how, like when everyone applied to college, this is how the process works. It's decentralized. You get your offers, maybe you get waitlisted somewhere, but eventually the process clears. And actually, in many settings, they use actual algorithm. So in the US and actually a lot of other countries now, medical doctors, when they finish med school, they are assigned through an algorithm to their first residency. And this is also used, if you've heard the phrase school choice, there are algorithms that match students in certain cities to the public school that they're going to attend. And once we start thinking about using an algorithm, it's maybe natural to ask things like, what algorithm should you use? And what properties should you want to evaluate if the algorithm did a good job? So just to get started, so I want to make this clear point that mechanism design is not algorithm design. So let me just explicitly state what would be like the purely algorithmic view for this problem. So, so if you've done algorithms before, you would say like, I don't know, this sounds like a matching problem. And you learn in pretty early on how to find the max weight matching in graphs. So just to be really clear, you can just make a graph and say on one side you have the doctors, on one side you have the hospitals, ask everyone for their preferences, and you do some procedure to assign a weight to every edge between a specific doctor and a specific hospital. Here's one on the slide, here's one specific way I might do it, but I'm not attached to this specific formula. But what this does is this gives me a weight for every possible edge, and I find the max weight matching. I say that's it. And I want to say, like from the practical perspective, I think there are so many problems with using this. So it's not that I think there's an issue with trying to assign a weight to the value of each edge. I actually think that's a realistic and practical thing to try and do. The problem is just by treating it as an only algorithmic problem, you run into a lot of potential issues. So one is that maybe the matching you produce is unstable. So what do I mean by that? That maybe there's a doctor in a hospital and the doctor says, actually, I like hospital H better than what I was assigned. And hospital H says, I like Dr. D better than what I was assigned. And then they're just gonna say, screw the algorithm, we're just gonna match with each other. Another thing that might happen is the players may say, well, this max weight matching is gonna happen. I think that I'm not likely to get my first choice because my first choice is very competitive. So I am going to pretend that my second choice is actually my first choice to make me more likely to get it. So that's a possibility. And it's actually pretty unclear how players should strategize if they were asked to participate in this. And so the behavior might be really unpredictable. And so what you get is that you certainly have found a max weight matching for the input you work with. But I would say it's not actually, doesn't seem likely to me that the input you get is going to be the input you really care about, because it's going to be so heavily manipulated for the incentives of the individual participants. Okay, so what I want to do now is I'm going to spend, maybe 20 minutes kind of going through different formally specified properties that you might want an algorithm to have. And what I'm going to do is just kind of state some results and try and make some connection to how this has kind of found its way into policy. But mostly what I'm going to do is I'm going to state some properties and kind of tell a little bit of a story through the results that have been proved in this field. Okay, so let's start with this first concern I mentioned, which is that, one thing that might happen is after the algorithm produces a matching, there's a doctor in a hospital that just say, screw this, we're, hospital says, I'm going to hire you. And the doctor says, yeah, I'm going to quit my job and go work for you instead. Okay, so let's just formally make that a definition. So we can say a doctor and a hospital are a blocking pair for a matching if the doctor prefers the hospital to their job and the hospital prefers the doctor to their hire. Right, so it says the doctor says, yes, I would prefer H to what the matching is telling me to get. Hospital says, yes, I would prefer D to what the matching is telling me to get. And a matching is stable if there's no blocking pairs. So this is kind of like an after the fact incentive constraint that says once the matching is there, no one really has an incentive to break off and do something else. Okay, and then the seminal result that kind of started this field, and Shapley actually got a Nobel Prize in large part for this work, is that stable matchings always exist. And there's actually a very simple algorithm to find one. So I will state that algorithm because that's going to be relevant for understanding some of the other statements I'll make. So the algorithm is very simple. It just says this. It says initially, no hospital has a hire and no doctor has a job. Then what happens? In the very first round, every hospital simultaneously proposes, so think of it as makes an offer to their favorite doctor. And then at the end of round one, every doctor tentatively accepts their favorite offer. And all the other hospitals get rejected. And so now you enter the next round, you have some hospitals that don't currently have a match. So they're going to make an offer to their favorite doctor that hasn't yet rejected them. And the doctors at all points are just going to tentatively accept their favorite proposal, including their match from the previous round and anything they got this round. And you just iterate this process until there's no unmatched hospitals. That's it. So that's the whole algorithm. At the end of this algorithm, you're guaranteed to have a stable matching. Okay, so the reason I bothered kind of stating this algorithm, so first, this is basically like the algorithm that gets used. So a variant of this is used for the residency match, and variants of this are used in a lot of school choice settings. It is not the only mechanism that's used. If you want to ask me for some other examples during the Q&A, I can describe some other examples that get used. But this is, I think it's fair to say, kind of like the most widely used, and where there's a lot of rich theory, and it's really implementing policy and practice too. And the other thing I want to emphasize is that, like I have a very broad view on, algorithms and protocols. And I would say, even for a decentralized job market where firms just make offers on whatever timeline they want, I would still say like, yeah, I mean, in some sense, that's a protocol or it's an algorithm. It's very disorganized and it's maybe hard to formally specify, but it's some decentralized approach to clearing a job market. And the deferred acceptance algorithm is basically like what's going on there, right? Where, firms who don't have employees yet, they make job offers. And, you as a potential employee, you get a bunch of offers and you reject the ones you're not going to take because it's not your favorite offer right now. And maybe you get better offers later, and then you turn down what used to be your favorite offer back then. So what this means is that analysis of deferred acceptance does imply some analysis of this decentralized approach too. Okay, so that was a key property one just to get started, that here is a formal property of stability. And I think it's important that algorithms have this property, and that was like one sample of a theorem. So let me describe a second, I mentioned a second concern, which is that, great, you have this algorithm, and after the fact, you might say, I'm not going to want to break off and form my own matching. But maybe there's something clever I can do in how I report my preferences to try and get a better match. So formally, the definition that we'll want to use here is I want to say that an algorithm or mechanism is strategy proof if for every player, no matter what the other players do, there's nothing that they can do better by lying. So what I mean by that is I'm not asking, for like all players that like they should get their first choice. So that's unrealistic. But I might say like, look, to player J, I might say like, look, based on what everyone else said, the best partner that you can possibly get is your fifth choice. And it turns out you will get your fifth choice by reporting your true preferences to the algorithm. So there's nothing you can gain by lying. Okay, and so you can think through that deferred acceptance procedure, and you might be able to form some intuition. And I would suggest maybe trying to quickly do this just to get more engaged in the talk is, as a proposer, you might try and think like, well, is there any incentive for me to propose to, my last choice first or my fifth choice first or something like that? And as a receiver, you can ask, is there any incentive you might have to reject an offer that's actually your favorite so far? So it turns out that the former is not possible. So for the proposers, there is nothing you can gain by proposing in any order other than your favorite. Okay, and maybe that's counterintuitive to some people. They would feel like, wait, if you're not going to get your first choice, then shouldn't you prioritize proposing to a hospital that you actually have a good chance of getting, or a doctor you actually have a good chance of getting? And it turns out that's not true, that the worst thing that can happen if you propose to some place that doesn't like you is you get rejected, you try again. On the other hand, it turns out that it is not strategy proof for the receiving side. So if you're receiving proposals, it actually could be in your interest to reject a proposal that is your favorite so far, and then you cross your fingers that somehow that triggers a chain where this place you rejected is now going to make an offer to some other doctor, and they're going to take this offer and they're going to free up a job that actually you wanted. And you hope that somehow that happens. That is possible. And so there's a follow-up theorem that says that actually no algorithm is strategy proof for both sides. So there's some trade-off. You can only get strategy proofness for one side. Okay, so what does this mean if you're actually trying to implement an algorithm like this in practice? So for residency matching, when you're matching doctors to hospitals, both sides are strategic, right? The doctors want, to get their best job, and the hospitals want to get the doctors that they like best. So what that means is, as a designer, one thing you have to choose is, if you want to run deferred acceptance, which side is going to propose. And I would say the implication is, one thing you should at least be mindful of is maybe which side you are more concerned with being strategic. On the other hand, for school choice, in the domains where it's used, like with public schools, the school preferences are not always like real preferences of the school. They're sometimes kind of coded into policy. So like, there's this thing called the walk zone priority, where students who live within a certain distance are supposed to be prioritized over others. And there are all sorts of other things that might go into this. Or at the end of the day, it might just be lottery based too. And so what this means is sort of like, well, maybe in that setting, you don't have to be super concerned about the schools manipulating their preferences, especially if they're just kind of codified by policy in the first place. But you might be more concerned about the students trying to get, the school that they like best. And so that might suggest that having the side that, the student side that actually has real preferences, that having them propose might be better from this perspective. Okay, so here's a third concept. So another thing that happens, unfortunately, pretty often in practice is that, I just described this algorithm to you, and I told you that it's strategy proof. So that means that you don't have to like trust me, you don't have to trust the designer. It is in your own interest to report your true preferences. And if you try to game it, you may be hurting other people, but you are definitely hurting yourself for sure. Okay. And despite this, there is a lot of evidence that people still don't report their true preferences, both in practice. So this lab experiments confirm this, and empirically, this happens in practice too. So, okay, so why might this be? So like just for context, right? So I teach the theorem I mentioned on the previous slide. I teach that in 445, so that's an undergraduate course. And it takes a full 80-minute lecture to give that proof. And I actually think that's one of the harder lectures of the semester. And, and this is to Princeton students, right? So you can try to imagine if it takes 80 minutes to convince, like Princeton students who are algorithm designers that a particular mechanism is strategy proof, then it may be hard to convince, just like all of the parents in a school district that actually a mechanism is strategy proof, or all of the doctors who participate in the residency match that a mechanism is strategy proof. So in line with kind of like what our field does, there was a formal concept introduced by Lee in 2017 to try and capture specifically not only when are mechanisms strategy proof, but when is it easy to convince someone that this is the case. Okay, so we even have a formal term for this. Okay, now that formal term is a little bit of a mouthful, so I'm not going to try and state it in this talk, but I can give you some intuition for like, what is it distinguishing between? So here are two mechanisms that I could use to match doctors to hospitals. And if you stare at them, you'll see that from, as an algorithm, they're really doing the same thing. But how I present them to you is a little bit different. Right, so first I might say, here's what I'm going to do. Doctors, I'm going to ask you for your preferences. I'm going to visit you in a random order. And then what I will do is I'll go down your list and I'll find your favorite hospital that's not yet matched. And then you just go there and you're stuck and you sit there and that's it. And it could be, that like for this audience, you look at that and you think for a little bit, and maybe it's not obvious that it's strategy proof and you want to give your true ranking. But I suspect that, you could reach that conclusion and maybe come up with a clear proof. But here's the second mechanism where it's much easier to see that. So instead, what I'm going to do, I'm just going to visit the doctors in a random order. I'm going to ask each doctor for their favorite unmatched hospital only when I see them. And then I will just match them to that hospital. And that one I think is much easier to see, right? I'm literally just saying, when I get to you, tell me the hospital you want, and I'm going to give it to you. So the second mechanism satisfies this definition of being obviously strategy proof, and the first one does not. Okay, and maybe unsurprisingly, since it takes an 80-minute, lecture for Princeton students to say why deferred acceptance is strategy proof, that is not obvious. And second follow-up thought, so this was investigated more recently, is for school choice, the designer has some flexibility in codifying different priorities into policy or law, and they can choose priorities and tiebreakers in such a way so that maybe for these specific choices of tiebreakers that I'm using, it actually would be obviously strategy proof and very easy for me to explain to the proposers that nothing funny is going to happen and you can't gain anything by proposing in a different order. So there was theoretical work by Ashlagi and Goncharovsky, and I'll point out Clay Thomas is a student here if you're interested in this. And they completely characterize the sets of priorities for which this holds, but it's pretty restrictive. So I think that is not likely to be a viable approach in practice. But some follow-up work to this is the same Clay Thomas, who's a student here, is there is ongoing work to formalize a more quantitative measure of how easy is it for me to explain this mechanism to people who need to participate in it. Okay, so let me give kind of like a quick summary here. So I told you, three formal properties: this stability, strategy proofness, and obviously strategy proof. And the three results that I told you, I said deferred acceptance produces a stable matching. It's strategy proof for the proposing side, but not for the receiving side. And it's not obviously strategy proof, which means that it's hard to explain to people why they should tell the truth. Okay, so what I'm going to do now, I am going to quickly just kind of tell maybe like two more stories that are, also policy adjacent. They don't have to do specifically with incentives, but I think you will look at them and still see a similar theme where like, here's a, here's a formal property. And it turns out that these like seemingly inconsequential algorithmic decisions actually have a pretty big impact on the output. Okay, so I just have these two examples. So example one is trying to determine how good is a match that you output. So the deferred acceptance algorithm finds one stable matching. And there's a lot of stable matchings though. So like there's possibly up to exponentially many of them. And you could have an algorithm that picks different ones in lots of different ways. And I don't know, there's a lot you can do. So let me try and also kind of ask like a teaser question to try and think through for a minute is just which side should propose. So we previously talked about the algorithm being strategy proof for the proposing side, but not the receiving side. But I also have some flexibility depending on which side proposes. That's going to produce two different stable matchings. And maybe one side tends to be happier with one kind of matching than the other, or maybe there's some in between. And in particular, I think it's not obvious unless you really think about, is it better to be proposing? Because if you're proposing, then you're kind of like going through your top choices quickly. Or is it better to be receiving? Because if you're receiving, then you have more information about what options are available to you when you're making decisions. And okay, so I saw there's a question. I'll get back to the question in a second. It has a short answer. So here's the main theorem here. So say that a partner is attainable for a player if there exists a stable matching where player I gets partner J. So what that means is that, for example, your first choice, while you might love to get it, there might just be no stable matching where you get your first choice. So I say, sorry, it's not the algorithm. That's not an issue with the algorithm. There's just no stable matching. But what turns out, and so this is also from that seminal Gale-Shapley paper, is that this deferred acceptance algorithm simultaneously matches every proposer to their favorite attainable partner. So that means simultaneously for every proposer over all stable matchings and all partners that they might have, every single proposer gets matched to their favorite partner that they could possibly get in any stable matching. And for every receiver, it's exactly the opposite. So they are getting their least favorite attainable partner. Okay, so initially, from like a philosophical point of view, I think that sounds very jarring that, that's a huge difference. And what you might care about, like for practice, is sort of like, how much does that matter? And there's a lot of theoretical work on this. So the first one that I'm aware of was by Patel in '89. And he showed that actually it matters a lot. So specifically, he considered a specific model for drawing preferences. And he showed that the proposers are going to wind up with their log nth choice on average. So if you think of like maybe n is 1,000 players, they're getting all in their top 10. And the receivers are getting their n over log nth choice on average. So again, thinking of n equals 1,000, this is like everyone's getting 100 or so. So this is a huge difference between proposing and receiving. However, what was noted is that this didn't seem to be bearing out in practice in the residency matching example specifically. And in 2005, Morlika and Madian provided a theoretical explanation for that. So they said, actually, if the number of potential matches is limited by a number of applications or interviews, then this phenomenon doesn't hold. So specifically, say that maybe the doctors send an application to at most K of N potential partners, and say K is much less than N. Then it turns out that almost all players actually have the same partner in all stable matchings. So what that means is that while philosophically it sounds like favorite to least favorite is a huge deal, that there's only one partner you can possibly wind up with anyway. And for almost everyone, they don't actually care which side proposes. They're going to wind up with the same partner in either case. Okay, and in practice, it did turn out that for the residency matches, there's data that I think on the order of maybe like a dozen or dozens of the thousands of people who participate actually would have had a different partner in the different proposing. And there was even more recent follow-up work that gave another reason why it may not matter, another possible setting where it may not matter which side proposes, which is maybe one side of the market is slightly larger. And so what they showed is pretty remarkable. So they showed that actually if one side has N players and the other has N+1, then it doesn't matter which side proposes. Almost everyone gets the same partner in all stable matchings again. And the other thing they showed is that basically it doesn't matter who proposes. It's what really matters is, are you on the short side of the market or the long side of the market? And that if you're on this side, which has N players, you are going to get your log nth choice on average. And if you're on the large side, you're going to get N over log nth on average. And that this dwarfs the impact of which side is proposing. Okay. So let me say one more example here. And I may actually, okay. So one more example here. I'll go through this a little bit quicker. So in school choice settings, again, I mentioned the designer chooses the school preferences. And no matter what happens, there's going to be lots of students who are tied by whatever metric you use. Maybe you even decide to just use a pure lottery and there's no actual priorities. And then you can ask, okay, how should you break ties? And my instinct, if someone asked me this question, honestly, my first reaction would be like, I don't know how you expect me to care about how you break ties. This sounds like such a mundane thing. Can you just like, I don't know, do it randomly, whatever that means. And someone might ask me, say, well, okay, I'll do it randomly. But can you just please formally specify, would you like me to have each school use its own lottery to break ties? Or would you like me to have a global lottery to break ties and just say that, if you wind up early in the global lottery, you're going to win a lot of ties everywhere. Or if you wind up late in the lottery, you're going to lose a lot of ties everywhere. And I don't know, my instinctive reaction might still be, I don't know, just pick one. Like, how is this going to matter? Or if you really pressed me, to not think mathematically, but just think intuitively, I don't know, my intuition is that like, it seems a little unfair to have like a single global lottery and then say, if you have bad luck in this lottery, you're going to have bad luck at every single school. So if you forced me to like use, very basic intuition, I would lean towards idiosyncratically, just seems like it's going to wind up being more fair. And it turns out that if what you really care about is the quality of the match, that intuition is not good. And so there's an empirical paper and then several theoretical papers too, that give pretty convincing evidence that it's actually better to use global tie breaking than idiosyncratic tie breaking. And in particular, one measure they use is just how many students wind up with their first choice, or how many students wind up with one of their top two, or how many students wind up with one of their top three, et cetera. And it turns out that by these measures, the matchings are a lot better if you use a global tiebreaker instead of an idiosyncratic one. There is some trade-off. So at least in the theoretical model, one trade-off is that depending on exactly how many applications get sent, you may wind up having more matches with the idiosyncratic tie breaking. But my understanding is that that does not seem to be relevant for the lengths of the lists that people see in practice. Okay, so I think I will skip this slide, but I'll just say that there are all sorts of other issues that are studied in this setting. One of these references is to a survey. I'm also happy if people are interested, I can point you to other surveys too. Okay, so to wrap up this part, so like stable matching has a very rich theory. It's very widely applied. The precise details can be very important. So they may seem insignificant, but they matter a lot. And then it's also really important that there's this deep theory that says, oh, for these kinds of domains, this quantitative impact is big, this one is not. And for these domains, it flips or something like that. And the reason for that is that there's sort of like no like ultimate optimal algorithm. There's always trade-offs. And so a lot of these works are good at understanding kind of like how sensitive is each trade-off to different aspects of the domain. So there was one question in the Q&A that I'll just quickly answer now, which was if there is a constraint on the number of choices proposers can make, so for example, the number of applications you can send, or you can only rank somewhere that interviewed you, would the algorithm be strategy proof? So the answer is, after you have sent your applications and after you have done your interviews and you are just deciding how to rank, then the algorithm is strategy proof. However, if you are only allowed to send 100 applications, then choosing which 100 applications to send, that requires maybe some gamesmanship that you should not necessarily, like for college, you should not necessarily just apply to your 10 favorite schools. You may want to apply to some safer ones. But once you have done the applications, done the interviews, you're just ranking, it is still strategy proof. Okay, can I actually ask one of the organizers whether I should pause now, since this is a good stopping point for Q&A, or whether I should keep talking?
Sure. Maybe if people have questions now, they can put them into the box, type it into the Q&A box.
I have a question, but it doesn't allow me to type in the box because I'm a host, I guess.
Oh, okay. Please go ahead and ask it then.
Okay, thank you. As a non-theorist, the most surprising part to me of what you said is that the characterization of obviously strategy proof is formal and not empirical. I understand why that is. At the end of the day, you have to prove theorems, but does this literature make any reference to empirical findings on what people actually consider obvious in practice?
Yeah, so that's a good question. Let me go back to hopefully I can do this quickly. Okay, so here I gave you two examples of mechanisms. And so I'm not an experimentalist, so I am not all the way up to date with like every lab experiment that's been done. However, for the lecture I give on this in 445, I did look up kind of like basic statistics. And this mechanism one, people in labs don't figure out that they should report their preferences in the correct order. And so like the lab experiment would be something like, I have a bunch of envelopes. Inside each envelope is some prize money. And, I'll tell you one of them is $20, one of them is $10, one of them is $5 or so on. Then I'll say, please give me a ranked order list of the, your favorite envelopes. And in lab experiments, people will put them not in decreasing order of the money. And they will do a better job at taking the envelope with the most money in mechanism 2. So specifically for the question of like the school choice, I would guess that sort of like, okay, so the fact that there's a theorem doesn't that is not the reason that it's ruled out. But I think it is just a very hard thing to do, to find a structured, concise way to convince like a large mass of people that something is strategy proof. So I can point to this work I mentioned that was going on with Clay, the student here, that they are trying to find some language that will say, this complicated mechanism is easier to explain than this other complicated mechanism, or this way of explaining this complicated mechanism is better than this other way of explaining it. But I don't know that the result of that is going to wind up being like, here's how we should have been explaining deferred acceptance all along, and here's how we should have been setting the preferences so that it was actually easy for people to understand.
Thank you. Very interesting.
Yeah.
Any other questions for the speaker? We have about 10 minutes left, so I want to make sure if people have questions, they should ask them. Okay. We have a question from Pranay and Churi. The question is, do these various matchings play a role in Bitcoin block proposal? Could you please give an example?
Yeah, so I think these, so this kind of theory, I am not aware of an application of this theory to cryptocurrencies. Depending on if there's not a lot of questions, I can share a little bit about my own work on cryptocurrencies, which is pretty different. But I don't have an example where of an application of this particular kind of stable matching theory to cryptocurrencies, or specifically Bitcoin block proposal. But I can say something about cryptocurrencies.
I have another question about, you mentioned that your group can act as sort of informal consultants. Maybe you could talk about that and your experience being more involved in the policymaking process.
Sure. So let me jump. Okay, so let me jump all the way towards that. So I'm skipping through a sampling of results. Okay, so, all right. So I mentioned that I like to think of us as potential consultants, and one of the people I've worked with in CITP, probably the most I've worked with Arvin. So I don't know if you can definitely ask Arvin for his opinion on what that experience was like. But just to be clear, I do want to contrast that, like, I definitely don't think of us as potential mercenaries. So like, I don't think you can just kind of be like, hey, we have a problem, and I think you can get a paper out of it if you solve it. Here's the problem, please solve it. Or even like, here's a problem, here's money, if you solve it, please solve it. I think it definitely doesn't work like that. But I think we work well with like a lot of collaboration and guidance from a domain expert. So like the way I like to phrase it is, I like to think of our group as kind of like, to the extent that we're experts in something, I think of us as technical experts rather than domain experts. And I feel like in order to have impact in a domain, that someone needs to have domain expertise. So some examples, that I mentioned, so I've collaborated a lot with Arvind and with other research groups in CITP. And those projects were research oriented and aimed towards conference publications. And so, what happened, so the domain expert in that example spent a lot of time explaining the domain to us. And, that was nice. I was very spoiled in that I got to learn about cryptocurrencies from Arvind. So that was great. And then, the process is there's a ton of back and forth in trying to even come up with like, what is the right problem to solve? So what that looks like is, I think, like our group and people with our expertise, we are good at coming up with models where you can learn something interesting about that model. But if you kind of want that to be relevant for a domain, someone needs to kind of be there and saying like, wait, this feels fundamentally different than the domain that you started caring about. And here's what's missing, and you go back and you change the model. And so my experience was that there was a lot of back and forth. So to the extent that there was like tons of collaboration, I feel like you know, 80% of the collaboration, or maybe 90%, was like all the discussions that took place just to like settle on what exactly is the problem that we're even going to try and solve. And I'll also just kind of put a pitch out there. I don't know how many like, you know, undergrads are in here, or how many people who supervise like IWs or theses here are. But another model that has been working pretty well recently is more of the scale of independent work or thesis project, is there's maybe some client on campus who, you know, fills the role of the domain expert and spends a lot of time explaining exactly the problem and making sure that, you know, the algorithm that the student is implementing is actually solving the problem they care about. And related to stable matching theory, some cases very recently that have been successful within the CS department, where I have access to, you know, lots of clients, is these are undergraduate students who designed algorithms for like matching lab TAs to shifts in our intro CS courses. And more recently, we've now tried to use the same kind of stable matching theory to design, you know, an optimization algorithm to match the TAs, graduate TAs, to courses in the CS department. And so projects like that is what's happened recently, but I think in general, that's like a pretty good recipe for a smaller scale type of project. And the other thing I was gonna say is I just wanted to quickly advertise the PhD students here who work with me, that all three of their names showed up for some results at some point during this talk. I focus on stable matching, so I think you only saw one of them. You know, but like I asked them all, they all said that they are generally interested in projects like this if the right one comes up. And if that interests you, you can reach out to them through me, or you can reach out to them directly. Or, you know, for any of the students who are listening, if you want to do this stuff yourself, there's a, you know, an undergraduate course that teaches this stuff, and you can join there too.
Fantastic. Thank you so much, Matt. We really appreciate it.